Welcome to qnawire.
Here we got these three different ways of basically shifting this panel. I guess they said it was a sliding panel. Shifting it over to the left by using some kind of weights and weight and a pulley. So the first case, we have this system here where this is attached to the wall. We have this cable over here, and then this weight is going to fall, and then that's going to cause this length to shorten, and then that means this has to go that way. But we also have contact here, so we got to be careful about that. And we're assuming it's frictionless, so that's at least a nice thing they gave for us in the problem. The second situation is this, and so obviously this just falls, that pulls that. This is a much simpler situation. And then this one here, this thing falls, and this accelerates this way. So we're going to assume that there's no contact there, or that the force here, if we were to calculate it, would be negative, so that there's no contact here, because this thing is accelerating that way. And theoretically, if this were, this thing would actually wind up swinging out. So there'd be no contact there. This one would want to swing out, but because you can't, we have contact there. So let's take a look at this one. This one actually is the most difficult. So our free body diagram of this panel, we have the forces from where it's hanging, its weight, the contact force between this weight and the panel, and then we have a force from here, right, we'll call T, and that's the tension in this cable. And then basically I took this as my free body diagram, and then we have the tension pulling down on it also. So in the horizontal direction, which is really all we care about in this problem, in this case, this is positive here, is T minus F equals the mass times the acceleration of the panel. And now we gotta look at the block here. Now the block has this tension T in it, which is basically the equal and opposite of this one, and then the equal and opposite force from the contact, and then its weight. And so in a vector, in the full vector form, we have minus F in the I direction, so I said that was positive, plus T in the J direction, minus its weight in the J direction, equals its mass times the acceleration vector of this block here. And that's what we don't know, because it's going down, we know, but it's also being pushed this way. So what do we know? How do we get that? Well, its acceleration is the acceleration of the panel plus the acceleration of the block with respect to the panel. And so the panel is going this way, right? And the block with respect to the panel is going down. And because of the length of this rope is unchanged, those two accelerations have to be the same. So the accelerations are the same, AP. And so that tells us, okay, so that's good. So we take in the I direction, we get minus the force equals minus the mass times the acceleration of the panel. And then this is in the X direction. In the Y direction, we get the tension minus the weight of this hanging block equals the mass of the hanging block, or minus, it winds up being because of this, minus the mass of that block times the acceleration of the panel, because that's also there. So what we can do is we can take this. Let's see, what did I take? I took this equation and subtracted this one and subtracted this one. And so that basically winds up, all of T and F all drop out. So I just basically use these three equations to eliminate T and F by subtracting these two from this one. And then what we get all left over here is just basically the mass of the panel minus twice the mass of the block. That's basically these terms. And from here we can just we know everything in here except for this acceleration. So we can plug everything in, and we get that is 8.94 feet per second squared. Once we know that, we can then just plug it into either here or here and get T, and that winds up being 18.1 pounds. So that's for that case. Now in this case is a lot easier because we don't have any contact here. So we just have, we know that the in the y direction, or in the x direction here, we have T equals the mass times the acceleration of the panel. For this guy, we just have minus T plus W plus its weight equals the mass times the acceleration of this block. We know that the acceleration, since I took positive down, positive here, these two have to be equal to one another because the length of the rope is unchanged. So that just gives us, we can use these, add these two, get T drops out, we get this equation, and solving that for the acceleration of the panel, we get now the acceleration of the panel is 12.4 feet per second squared, and the tension in the rope is 15.4 pounds. And so one thing we can look at is that this is less than this. And does that make sense? It does, because now we're basically not pushing this, block. Basically, the inertial load of this block is less in this case because it's just moving down here. Here it's moving down and to the left. And the tension is less because the accelerations are essentially greater. There's not as much load on this because of the inertia. So, it seems like this would be a much better setup, so you don't have things rubbing there. This seems like another setup, and we'll take a look at this one too. Turns out this one and this one are identical, just because all we've done is shifted where T acts. Right? So this seems like the best setup because here you got a long cable, and it's crossing over there. Anyway, this seems like the best setup, but we can look at this one too, obviously, and we can see here that we just have T, and then we have T here, right? And then we have the weight and the loads from where the panel is hanging. So in the x direction, we just have T equals W, the mass of the panel times the acceleration of the panel. This guy, and that there's no contact force, so that's gone. So we have this, that because just from kinematics. And then this is proved by Newton's laws for that, gives that. And so we can see that basically we just wind up with this again, exactly the same. Because all we've really done is change T, where before it acted here and now it acts over here. Now we've also acted, that's another negative for this design, is we have this T acting down here too, which means that these things are going to have to be greater forces because they're going to have to offset both of those. And over in this case, there's no downward force from the, we just have to, there's a downward force on this guy, but we don't really care about that. In fact, it'd probably be better to have, kind of this at an angle there. So we can see that this situation gives the same exact, at least for how this panel moves, exactly the same as this. Now the forces holding the panel up are going to be greater here. So it's all the same math. So we get 12.4 feet per second squared and 15.4 pounds in the cable. So again, we're going to add some load to these rollers at the top. And I guess I forgot to write down what the weights that were all of these things. So actually, let's get that down here. So W2 was 40 pounds, and W1 was 25 pounds. So what's going to happen here is, in this case, the loads here say it's evenly distributed, which it wouldn't be, but just in general, we're going to have extra 7 pounds, so we're going to have to support 55 pounds with these rulers in this case, and only 40 pounds in this case, because this load, some things are supported then by this little side, this little roller support over here. So we're distributing the loads